All right, welcome back, everyone. I'd like to start class today with something that happened last class. Do you remember I said I had a complete brain fart? It was this problem right here. What we had done was, if you have your take-homes, just put them here. What we had was, we were trying to show that this line integral of this vector field, you want to staple it, that the line integral of a vector field given by this right here over any curve C that enclosed the origin was equal to 2 pi. So I went through this thing and we created this C prime and we went around and we were able to use what I'd shown you just before that to compute this damn thing. And it came out to be this double integral, and that double integral, when we put the partials in there, it came out to be 0. And so we were able to say that these two line integrals subtracted were equal to 0, which means they're equal to each other. And then on the next note, I said, okay, well, if they're equal to each other, let's find out what the one around that little circle that we created, let's find out the line integral there. I said, okay, well, since it's over a closed circle, let's just use the double integral again. But if we do the double integral again, we would get 0 again because the partials are the same, aren't they? I said, what the hell's going on? So I did it this way, the other way. Now, here's the reason why, and I don't know why I didn't pick up on this last class. The theorem that we were using, 13.5, where the hell is 13.5? It's 13.4. Here we go. The theorem that we were using right here, that I was going to use, says, let C be a positively oriented, piecewise smooth, simple closed curve in the plane. Let D be the region bounded by C. If P and Q have continuous partial derivatives on an open region that contains D, then there's the relationship. Well, guess what? P and Q do not have continuous partial derivatives on the region that I was going over right here. It does not have a continuous partial derivative on this region because that region includes the origin 0, 0. And at 0, 0, our vector function is not defined. Our vector field is not defined. Right? Go back one. This vector field is undefined at 0, 0. And so is its derivative. So that's why we cannot, that doesn't mean that we can't compute the line integral. It's we can't use Green's theorem to convert it from the line integral to the double. So we're forced to do it the other way. And that just went right over my head yesterday or the other day. And we still got the answer, but I was kind of like, well, wait a minute, why didn't we just use double? Does that make sense now? Okay, so I just want to clarify that because it was really bothering when we left class. All right, today, we are going to start with parametric surfaces and their areas. So what I have for you is a handout. Hopefully this came out okay. I haven't double checked these to make sure they printed properly, but you can tell me. We are going to start out by not looking necessarily at the notes yet and going off of this instead. I did get your emails. Did you bring the hard copies of those today? Okay. One of the most challenging, if you have an extra, one of the most challenging parts of the remaining sections is making sure that you have an understanding of of how to take a surface and find its parametric representation. Because if you can't do that, then you can't do any of the calculus that's required in the problem. So this is like the fundamental. It's kind of like setting up a type 1 region, type 2 region. You have to know how to do that before you can do any of the double or triple integrals. Make sense? So let's look at this handout and look at the first example. Where's the example? Did I get these printed out of order? Is example A missing? It's all right, I'll just put it up here. Example A. Here's example A. Let's say that we have the X, Y, Z three-dimensional coordinate system, and I want to draw I would like to draw a circle that is parallel, the circle is parallel to the XZ plane. That makes sense? My picture's not that great, but in fact, you could argue it's terrible. Huh? That's supposed to be parallel to the XZ plane. XZ plane. And then the center of it is through 0, 0, 0. Okay? You know, yeah, but you know, I think I have. There we go. There. That's what I want. Okay? Got it? You see that? Okay. So working with that, it has a radius of 2. I would like for us to come up with a way of drawing that entire disk, not only the edge, but everything inside of it, with a vector function. Now, when we go back and we look at vector functions from before, R of t equals, we could have a 2-component vector function, or we could have a 3-component vector function, right? R of t. What did this draw? What do vector functions like this draw? They draw lines, also what? Curves, right? In 2- or 3-dimensional space. But their lines are curves. They're not surfaces. So I need a way of coming up with the way of drawing the entire surface with the vector equation. So what we're going to do instead is, instead of having one parameter, just t, we're going to have 2 parameters. So our new style of vector function now today and for the rest of this class is to define a new vector function, R of u v. And it will still either be 2 components or it could possibly be 3 components. But depending on how I manipulate the u and the v and these components of the vectors, I should be able to draw surfaces with it. Okay? So let's talk about this circle. Tell me about anything you know about that circle. Do you have an equation for that circle? I'm saying the outside of it. Do you have the equation of that circle? It's radius 2. X squared plus z squared equals 4, right? Y'all agree that would draw the circle, correct? Now, how would we draw a circle using a vector equation like R of t? How do we do that? We use cosine and sine. So if we were just trying to draw that blue part, and I'll write it in blue. If we just wanted this blue, we would do R of t. I don't think I want to move this down. We would do R of t equals what? It would be 2 cosine t. Now be careful here. I have to draw this blue curve in 3-dimensional space, right? So it's laying flat on the xz plane. So what's the y component of my vector function need to be? 0, because I need to hold my y constant at 0. Does that make sense? Okay, and then what's my z component? 2 sine t. Does everyone agree that that would draw that blue circle in three-dimensional space? It would draw that. Yes? But what this lacks is the filling in of the inside, right? In order to fill in the inside, I would have to change the radius of the circle, wouldn't I? So imagine just making the radius smaller and smaller and smaller, all the way down to 0, or then all the way back out to 1, right? Or to 2. So the 2 in front, if I could somehow manipulate that 2 and let it vary, then it would draw all the circles and create the disk. Agreed? So now let's go into this new vector function, which is going to allow me to control 2 variables instead of 1. I will write it as r of uv. I should have put up here next to the r of t. What was our t between? 0, 2 pi. That would have drawn it, right? So with this new idea, r of uv how about this? Can I put cosine v 0 sine v? I'm leaving a space in front of them. V is between 0, 2 pi. That would draw a unit circle, right? Because the radius of this would be 1. But I want to control that now, right? So the other variable that I can use to control it is the u. So if I put the u in front here and the u in front here, won't I be able to manipulate how big the circle is? Yes, I mean, you could look at it that way. You have control of the theta and the r in this case? You do? I mean, that is a polar region, isn't it? Yeah. But see, not all of the problems are going to be circles and disks, so we won't be able to use that general polar concept. Okay? Now, what's my restriction on u? 0 and 2. So what if u is 0? What if u is 0? What do I draw? The origin, right? If u is 1 and I let v vary, it's going to draw circle radius 1, right? I let u go up to 2, it's going to draw circle radius 2. And so with all the different radii between 0 and 2, I get the whole disk. Yes? All right, that is our first example. So the question here, it doesn't say it here because I didn't print that page, but our question was to find the vector function which would yield that surface. So we just found it. Okay? This is it. It's a new way of drawing a surface, isn't it? All right, the next question, you do have that one, right? The next one is find the vector functions, plural, which yield the 4 face surfaces of this tetrahedron. So we have a tetrahedron. I give you the vertices, and it's going to be a little bit challenging to draw that. Let me just bring it up here so you can see this. Right? We have tetrahedron like this, got a bottom to it. So 3 of the sides are parallel to the coordinate planes, right? But then one side of it is actually kind of a skewed plane, isn't it? So I want to be able to label these. Now, up here you can see like the blue one and everything else on your paper you can't. So the blue one is the one that connects the point, the origin to the point, what, 300 to the point 002, that plane. Let's start with that one. We'll call that surface 1, S1. Let's find the parametric representation of it. Sound a good idea? Well, we may not even need that much for this one. S1, I'm going to look at it. Now, notice I'm going to label my axes. This was X, this was Z. It went out to 3 on X, didn't it? 1 out up to what, 2 on Z? Can you come up with a way of drawing that for me using a vector equation? Now, and we are in three-dimensional space, aren't we? The surface is three-dimensional. So I will have 3 components to this. What component do you know for sure right off the bat? It has to be something. Y has to be 0? Y'all agree? Y is 0 because we're flat up against the XZ plane. So my Y is 0. Now what? X is what? Let's look at this is almost like a type 1 region, isn't it? I mean, go back to like type 1, type 2 regions. Type 1 here, we would say X is between what and what? 0 and 3, and then Y is between, I mean, not Y, in this case it would be Z. Z is between what? 0 and whatever that line is, right? Let me just kind of jot those ideas down over here. Right now I know that if I let X be between 1, not 1 and 3, 0 and 3, I could let my Z be between, what is the equation of that line right there? Z equals negative 2/3 X plus 2. Right, slope is negative 2/3. Y-intercept, Z-intercept is 2. So that would give me that, right? So what's my Z between? 0 and negative, that equation, 2/3 X plus 2. So now let's talk about these components. How about my X component? It could be, let's call X like the U, okay? And that U is going to be between where and where? 0 and 3, between 2 constants. So I'm going to let this one right here just kind of treat it like it's the X. I'll call it U. And my U here is going to be between 0 and 3. Now what about my Z component? My Z is like my V, right? My V is like my Z. So I could just call this V, right? But V has to be stuck between where and where? 0 and negative 2/3 U this time, because I've switched everything over. U plus 2. And this is it. To draw that little triangle in three-dimensional space, I use that vector equation. I let my U vary between 0 and 3, and I let my V vary between 0 and negative 2/3 U plus 2. Make sense? If I do that, I should be able to draw the whole thing. All right, what about, that was side 1. Let's do the other side. So I'm going to just keep rotating around like this. Okay, so this is my y-axis. This is my z-axis. I go out to 4 and then up to 2, right? Out to 4, up to 2. Also, on here, because I have 4 different surfaces, can we label this one R subscript S1? Y'all see me put that right there? That way we know that's the vector equation for the first surface. Now the second one. So what does my picture look like this time? My y-axis, is my point out on the y-axis positive? Was it positive 4? Yes? So I put out positive this way, and then it goes up 2 again. This is going to be very similar to the last one, isn't it? This is still my z-axis. I want to try and fill this thing in. What's the equation of this this line right here? Negative 1/2 y plus 2. What's my restriction on y here? 0 to 4. Restriction on z? 0 to that equation again, right? Negative 1/2 y plus 2. Using that idea, I'm going to come over here with the vector equation of S2 of uv will be equal to, which one of those components is the easiest one? X is 0, because now we're flat up against the YZ plane, so our X must always be 0. What's my Y going to be? U or V. I'm glad you said or V. You could use either one. It doesn't matter. I'm going to say U. And then what's my Z component going to be? V. My U will be stuck between the two constants, 0 to 4. My V will be stuck between 0 and negative 1/2 y plus, not y, sorry, U plus 2. Questions? How about the bottom one? How about the bottom one? We'll call that S3. You know what? Before I move to S3, let me point something out here that you could do that would not change the problem. This V is a function of U, isn't it? That V is a function of U? It depends on U. You could, if you want, replace this V with negative 1/2 U plus 2. And now what you'd have is a vector equation that would still draw the same surface, except you wouldn't have this anymore. In fact, your vector equation wouldn't have V in it at all. So you could actually draw that part with just this information and that information right there. Just pointing it out. But it's better to keep the U and the V in the problem the whole way. I think it works. Things work out a little easier. With the first one, we couldn't have, because the variables were controlling both the radius and the angle at the same time, so it wouldn't have worked out. Next, that bottom one. So I think for the bottom one, I'm going to look at it like this from the top. So we go out, what, 3 and 4? 3 on the X, 4 on the Y. Isn't that what it is? Three on the X, 4 on the Y. Got this. My X is between. Well, do you think you can go straight to it now? All right. This is equal to. I will label it. It was X and Y here, right? So which variable is 0 in this problem, in this particular case? The Z. The Z is the 0. The other two are just U and V, right? My U is stuck between 0 and 3. My V is stuck between what? Negative 4/3 U plus 4. And this is S, I forgot to label it. This is S3. And I've saved the more challenging part of it for the last one, all right? Because now what we need to do, were there any questions? We need to get this surface here. Hold on, this thing is not cooperating. try and get it to come back to me a little bit here. We need to get this skewed plane, right? This skewed plane. So how the hell are we going to get the skewed plane? Well, first let's find the equation of the plane. Can you find the equation of the plane? Well, I give you, you have 3 points, right? So you create 2 vectors, cross them out, get your normal, use a point, you get the equation of the plane. Not going to go through that work, okay? Do you agree I don't need to go through that work? Okay, so for S4, it's an angled plane. The equation after you do the work is 4x plus 3y plus 6z equals 12. Now that plane that we have that's skewed goes down to the ground, right? Down our x-axis, our y-axis, and our z-axis, something like that, right? If you are on that plane that's tilted, your x's and your y's, right? If I'm on this plane, my x's and my y's have to be stuck. I'm trying to look at it from the top again. If you're on this plane, right, that's tilted, your x's have to be stuck between where? 0 and 3, and your y's have to be stuck between, well, that thing that we had before, right? Right, it's going to be on this triangle. So it's the same restrictions we had earlier. So our x is going to be u, our y is going to be v, our x is between 0 and 3, our y is between, in this case, what is it? 0 and negative 4/3 u plus 4, right? But what about z? Yes, we go back up here to this right here and solve for z, and then what's x? Well, for us, x is u, right? And for us, what's y? It's v. So here's what it'll look like. R of uv it's kind of like this. U, V. U is between 0 to 3. V is between negative 4/3 U plus 4. And this is S4. Do you understand that if I just do this right now, this will draw me that triangle on the ground? Yes? Well, not on the ground, because this is not 0. Before it was 0, right? And that drew it on the ground. I don't want to draw it on the ground, do I? As U and V change, I want to be up on the plane, drawing points up on the plane. So my Z coordinate needs to be determined by these two. So solve that thing for, solve that equation up here for Z. If you do that, what do you get? Z is 2 minus 2/3 x minus 1/2 y. That's what you would get, I believe. Yeah. And then now that's going to go in for our z component, but we have to replace x and y with what x and y is. So x is u and y is v. And we're there. 2 minus 2/3 u minus 1/2 v. This should draw that. Questions? We'll look at something real quick. I don't remember how I had the computer draw this. Oh yeah, it was different. All right. Next example, example C. I want to draw this cylinder. Now we know the equation of this cylinder, well, if we know its radius, Can't really tell what its radius is. Let me turn it to the side so you can see it. What does it look like that radius is? 1. Oh, did I put the equation on there? Did I put the equation on there for you? Oh, then never mind. You know what the radius is. How far does that cylinder thing come out? 4. Again, you can't see it from your picture very well, but can you kind of see it from here? Right? And, oh, where does it start? 1. Couldn't really tell from here, could you? Everyone have a good picture of what's happening here? So how are we going to do this? The equation is x squared plus z squared is 1. I can convert that to like a polar thing, right? Where I let my x be what? X is, okay, r cosine theta, but here what's the radius going to be? 1, and then I can't use theta because my vector function needs to only use u and v. So my x coordinate should be just, now is it u cosine v? Look at the picture. Am I trying to fill the inside of that cylinder up? No, right? I just want the outside edge of it, right? So all I need to do there is have strictly cosine u or v. I'll go v. And then my z coordinate should be what? Sine v? And what's my v between? 0, 2 pi. Okay, right now, what does this draw me? What does that draw me? Circle radius 1. Now, where is it? Well, I haven't told you where it is, right? See, all I've done right now is I've drawn like an outer ring here, but I haven't told you where I want you to put it, right? Because the y variable is free, so the y moves back and forth this way. So where do you want me to draw that ring that we just drew? Where do you want me to draw it? All the way from 1, all the way until you get to 4, right? So your y coordinate needs to vary between 1 and 4. Now, y is not the variable we're going to use because we're stuck with u's and v's. So my y coordinate, what should I call it? U. And then I just restrict u between 1 and 4. Everyone see that this will draw that surface? I want you to see the difference between this problem and the one we did when we drew the disk. When we drew the disk, our u was in front of the sine and the cosine, right? And this other component was fixed. Here, the radius is fixed, and this one is free to go. So it's like we drew a circle. In the first example, we drew a circle, and then we let the various change, so we drew the disk. Here we drew a circle, but we fixed the radius, and then we moved it back and forth, which drew the cylinder. Can you do both at the same time? Could I draw that as a solid instead? We would need a third variable. We need a third one, right? But we're not going to do it here, okay? But that's why these are called parametric surfaces, because they draw surfaces. You won't be able to draw a solid with one of these. Just like the parametric curve, R of t, you could draw curves, but you couldn't draw surfaces. With R of uv, you can draw a surface, but you can't draw a solid. You could draw solids, yes. We won't do it in here, but the idea is there, yes. Mm-hmm. How does what? How does, you could take out the V and just leave the U. Back here? This one? No. look at this, your V coordinate right here is stuck between these two, right? And that's dictated by this. So like if U is 0, I get 4, right? If U is 3, I get 0. So if U is 3, that takes me all the way down here. U being 0 takes me all the way up to 4. So I would, I don't know if I'm making sense with this. You would have to, let's say you want to draw this point right here, right? That's U is 1, right? And let me write the other one down. U negative 4/3, U plus 4, 0. This is what you're asking me, right? How does that not draw? What would this draw right here? If I fix U to be 1 right here, what would this draw? It would draw that point, right? Okay. And then your see, but your V you have to have control over what this can be, right? That V. So if I let U be, let's say 2, then I should draw that point, right? 2, 8/3. No, that would not draw that point, would it? U is 0, you're at 4. I see what you're saying here. Hold on. Yeah, but it's not stated here like this. If U is between, see, we're not saying in this right here, we're not saying it's everything from 0 to that, right? So it's not everything in here. Let me look at this again. That's why I said leave it always UV. I've seen it switched. But see, we did it here. This Z coordinate is a function of those two, but those two, see, this is everything between the two, right? Okay, so just for now, I think you're on to something there. Let me go back and look at it. I don't want to take up too much time going through it now. Okay, what's the next example? Same thing. It's hard for you to see it, so let me show you mine here. Find the vector function R of UV which yields the red end cap of the cylinder shown. So I just want this end cap here. It's another disk. So what would it be? So what would that be? R of UV. What do we want the radius of our circle to be? We want it to vary, don't we? We want the end cap, so we want it to vary. So we're going to use, we could use U cosine V for the X coordinate, and then for the, what other coordinate do we need to work with here? Z coordinate should be our U sine V. That should draw me the disk, right? As long as I restrict my U between 0 and 1, and my V, of course, can be between 0 and 2 pi. But now I need to fix that out the y-axis at, what, 4? So I just fixed that center variable at 4. That should draw it. Now, what is the point of all this, right? We'll get to it. Yeah, I know. I don't know. I've been having all sorts of trouble with the printer lately. So let me just show you what it's supposed to be here. I'm going to have to draw it. Okay, so for, let's see. So we have B, right? We've got A, we did that one. We got B, we did that one. We got C, we got D. We just don't have E on your page, right?
No, but I mean, what is C asked for? Oh,
Yeah, that blue cylinder part. That's all it wanted. Draw that hollowed out cylinder from 1 to 4 on the y-axis. So we got that. D just wanted the end cap. So here's what we're going to be doing. We're going to have a surface that encloses a solid, and we're going to be calculating basically like the flux or the amount of flow through the whole surface. So what we need to do is compute that flux thing on every surface. So we have to be able to find parametric representations for each surface to do that computation. So that's our goal here. So part E, I don't have it up here. We'll come back to E. Why don't we do, you do have F on your thing, right? So there's two surfaces here. There's like this cap, and then there's the bottom of the cap, right? Cap on top. It's like a, what is that like? A what? Yeah, oh, okay. I was going to say it looked like a piece of candy or something. I was trying to think of a piece of candy. I was thinking dots, but whatever. But you have a surface on the top, and then you have the bottom of it also. We have to look at that. So why don't we start with why don't we start with the bottom first? I think that one will be the easier of the two. Can you tell what the radius of that is? It is a circle, isn't it? It is one. How do you know it's a circle? How do you know it's a circle? Look at the equation up here. That's the most important thing, right? It's where that surface hits the xy plane. So if we let z be 0 there, move things around, you get x squared plus y squared equals 1. So that is the unit circle on the ground. So for this one here, I'll call it S1, and then this one up here, I'll call S2. For S1, we have what? R of UV. You're trying to draw a disk, right? You want to fix your z to be 0. And then you want to draw the whole disk, so you're going to use u cosine v, u sine v. So u cosine v, u sine v. U is between where and where? 0 to 1. Of course, v is 0 to 2 pi. That should draw me that little disk on the bottom. Now I need S2. What about S2? What's the only difference between S1 and S2? I mean, the x's and y's on S2 are the same, aren't they? Look at it from the top. If you look at the top of that surface, the x and y's are exactly the same. It's just that you don't want your z to stay fixed at 0. You want your z to come up. And that z, how far you come up, is going to be determined by your x and your y, right? But you have the equation for it. So we're pretty much there. So S2, R of UV, the x and y's stay the same. But your z is now what? What is your z? 1 minus. Okay, so yeah, what you're going to do is you're going to take this up here. That's what z is. I'll switch it up here. It's 1 minus u squared cosine squared v minus u squared sine squared v. But you could simplify that, couldn't you? You could factor a negative out. That's u squared cosine squared v plus u squared sine squared v. Actually, I probably should have pulled a u squared out too, right? But that'll just turn into what? 1 minus u squared, right? The sine squared v plus cosine squared v will turn into a 1. You'll still have the u squared there. So this is just 1 minus u squared. Restrictions on U and V are the same as before, aren't they? Questions? Okay, let me go back to the example that didn't print out, which was E. So for E, what if we had this picture? It's going to be somewhat difficult for me for you to draw, but this is it right here. We're going to do that one. I need to tell you what everything is, but here's the picture. Oh, that didn't work. Paste picture. There we go. Okay, let me label some stuff because this has to be given to you. This right here is z equals 1 minus x squared. This right here is y plus z equals 2. I think everything else you can make out. Like this comes out to 2 here. This comes out to 1. This comes up here to 1. Can y'all tell what that looks like? I mean, it's kind of like a like a it's like a piece of paper's been folded over, right, like this, but then you cut it at an angle. And then the back part of it, look, is flat. Do you see that back part is flat on it? How many different surfaces do we have here? We have, let's say, the back side of this, that's 1, right? The front side, that's 2. This curved surface, that's 3, and then the bottom of it, which is 4. Yes? So let's find the parametric representations for all 4 of those surfaces. So we should label these. How about this is S1, this is S2, the bottom underneath there, S3, the back side over here, S4. I think S3 is the easiest one to do, don't you? S3? What's S3? I mean, well, S4 gets easy too. The bottom of the whole thing, what shape is that? It's a rectangle, isn't it? It's a rectangle or a square? It's actually a square, but it's neither here nor there. You got that? You see it from the top? It's too wide, too tall, right? So with S4 or S3, we know that R of UV will be equal to, well, my X's are just stuck between 2 constants, my Y's between 2 constants, and my Z is what? 0. So the way I'll write that is U, V, 0. U is between 0, 2. Well, it depends on what X is. X is the red one, sorry. -1 and 1. And V is the green, which is 0 to 2. Yeah, the x-axis is down here, is coming out this way, and the y is this way. I like this picture a little better. All right, what about let's do the next one that seems the easiest. How about S4? And this was, I'll call this S3 there. so there's S3. How about S4? What are you drawing on S4? I made this really narrow and it looks weird. Look at that backside here. It's not a circle, right? It's not a circle. It looks like it might be because it's one on top and one's on the sides, but it's parabola. So can you tell me a little bit about the actual? What's always zero there? Y is always zero, right? So let's start with that. So my R of S, where am I? 4 of UV will be my Y is always 0. And then when you look at that from the side, let me draw it. This is the x-axis, right? This thing goes like this, comes down. Yeah, what's the equation right here? Z equals 1 minus x squared, isn't it? Isn't that what this is? You get that from that blue part that curls over, right? So I could just say my x goes between where and where here? Negative 1 and 1, right? And then my z is just between 0 and this curve, right? So I should do this. I should call my x, let's call it u. That's going to be trapped between negative 1 and 1. But then my z coordinate is v. All right, it's v, it's something. But what is that v stuck between? 0 and 1 minus u squared. Does that make sense? All right, so that's S4. How about S2? Do S2? So let me look at S2 from this side right here. That's what S2 looks like if you're looking at it straight down the y-axis, right? You're standing on the y-axis, you're looking straight at it. So doesn't that very much look like the one we just did, right? Isn't that very much like the one we just did? Is drawing this parabola, what's the difference though? Your y-coordinate's going back and, well, not back and forth, but as I start to draw it from the bottom up, the y-coordinate starts to go away from me, right, if I'm standing out here? So somehow that y is changing. But I gave you the equation, didn't I? See, that y is a function of z, isn't it? You could say y is 2 minus z. So let me start to write this out. This is S2. So R of S2, I need to still draw the same parabola in the xz plane that I just drew. So what should stay the same is the u and the v on the outsides, right? The first and third components. But my y component should be controlled by this surface. Solve that for z, or for, yes, solve it for z or y. Sorry. Solve it for y, and you get y is 2 minus z, but z is v. So 2 minus z. Then what? Same restrictions we had before. U is negative 1 to 1. V is 0 to 1 minus u squared. That's your other surface there. Is it clear to everyone that the u and the v and these restrictions still drew that same parabola looking thing, but then by not flattening it out to 0, by using that plane equation and solve it for y, we were able to move it away and towards us, depending on where we are. Okay. And then now the last one, which would be this right here. So how are you going to draw that surface there? Turn things here. Let's look at it from maybe this point of view. That's from the top, right? Our x could be u, like this. U is between -1 and 1, right? And then our y is between what? 0 and whatever this is, right? Yes? And then what about our z? Our z is coming up at us, right? This curve, we got to get the curve involved. So our z coordinate is going to be somehow dictated by that parabola equation. So help me out. Let's see. I'm with you. Hold on. This was S1, right? So R of S1 you want your x to be u. What are your restrictions on u then? -1 to 1. Do you all agree with that? Then we wanted our y to be v. Okay. So y is going to be v, but it's stuck between what? 0 to what? What is it? There's multiple ways you can do it. You can draw it different ways. So you're suggesting now not to put v as y? What do y'all think? I mean, z is a function of x only, right? So z would be what? 1 minus u squared? Could you do that? That'll move you up and down. But we still need the restriction on v, though. You would have to find the equation of this right here, which is where the plane intersects that parabola thing, right? So maybe that won't work as well. Maybe we need to look at it from a different point of view. Okay, maybe we do something more like looking at it from here. Look at it from the side again. Can you draw me just the blue part, so not the stuff inside, just the blue part? So what would your x be between here? -1 and 1, so we're still could leave the u that way, right? What would your z be between? 0 and 1 minus u squared, right? Or 1 minus x squared? Now, everything between it? You just want the outside, right? So how do you do that? I think we can all agree on this. Can we all agree on that? Well, what we aren't agreed with is the rest of this, right? Hold on. Say it. Okay. 1 minus v squared. Is that what you're saying? V. 0 to... I'm just following what you're saying. Is it you want me to stick with this? 2 minus... You want that here? 2 minus... Yeah, I can't. That's not going to work. I'm backing up. Okay, come on. This is what makes this a little challenging. So come on. I mean, we have to. What is what is y going to vary between? If you're on this surface, your y is always like, let's say you want to draw this right here. Your y is between where and where? 0 and the plane, but what's the plane? Solve for y is 2 minus z, right? So you're going to go from you have an x value, right? That's between -1 and 1. Then you have a y value. What's your y value? What's your y value? Look, I'm trying to get up to this point right here. Look, draw me this line. Draw me the line that goes from that point across to this point. Draw me that line. So how do I get to that point right here first? Pick some x value, right? Then what's the y value? No, I'm not. I mean, the z value, sorry, is what I meant. The x is something, right? The z value is exactly 1 minus x squared, isn't it? And then my y value is everything between 0 and what? 2 minus z. But what was z? It was 1 minus x squared. Okay, I think we're getting there. Do y'all kind of see this? My x can go between -1 and 1. Once I pick an x, I have to get up to the blue curve. I don't want to be everything in between. I want to be on the blue curve, don't I? And then I want to vary everything this way. And then stick myself between y equals 0 and 2 minus z. All right, let me try that. So are we okay with this part of it? Yes? But what is my z value? Okay, my z value is exactly 1 minus u squared. Yes? And then what is my y value? Or yeah, my y component. What is my y component? Could you say this? Could you say it's v? And then what was v between? 0 to what? 2 minus, coming back up to here, it was v is our y, so 2 minus z, but what's z? 1 minus u squared, so 2 minus 1 minus, so plus u squared. So that's just 1 plus u squared. Yeah? What do y'all think of that? It's easier than I made it? I can't hear you. Yeah. But I think that's the biggest challenge, though, is that you can't just start throwing things around and said, yeah, that should draw. Sometimes on these you have to think through. If it's just a disk, okay, there's not a whole lot that we have to do there. But if it's something like this where not only was the x well, 2 of the coordinates were controlled by the x, right? This one was controlled exactly by x. Whatever x was, determined this exactly. But then this one varied. So you just have to be careful with these surfaces. I guess that's the moral of the story. We're done. Parametric surfaces, we have some idea of what they are now. We have some idea of figuring out how to get their equations. And now we can begin the notes for today. Okay, parametric surfaces and their areas. Most of this I already talked about. First part of this is just saying that, look, back in the beginning, we had vector equations that drew curves, right, in 2 or 3 dimensional space. Now we have this new thing, R of u v, where x, y, and z components could possibly be functions of just u, just v, or both u and v. This will give us a surface in 3-dimensional space. If you hold u or v constant, then you can draw out what are called space curves. So if someone gives you a parametric equation with R of u v, and they give you restrictions on u and v, then you can hold u to be constant and let v vary, and it'll draw a curve, right? If you hold one of them constant, then you're back to what we did before, and you just draw a curve. If you then move that constant to a different value, draw again, you'll have another curve. Draw all the curves, you get these space curves. And that can help you graph these things. So here's the first example in the notes of a parametric surface. It's sine u, cosine v, sine u, sine v, cosine u. U between 0 and pi, v between 0 and 2 pi. And do you recognize this, is what I say. So y'all recognize that? Maybe, maybe not. Sphere? So if I hold u constant and I vary v, I draw a circle. Let's go back to this. Hold u constant. Then that's a constant, right? That's a constant, and that's a constant. So I have a constant in front of cosine v, a constant in front of sine v, the same constant, right? Same constant? So that should draw me a circle. This should draw me a circle with radius what? Sine u, whatever the hell that is. And then this, cosine u, is a constant, that's my z value. So you can see from this picture that what's happening is that by holding my u constant and letting my v vary, I draw a circle that has a fixed z value, right? And it's drawing a circle with a specific radius. If I change the u, it should change that. I only have one of these. Oops. Okay. So if I were to change my u, I would come down to a different circle and draw that circle. Different radius, but still fixed constant z value. Start putting all these together, then you get, starting to get the sphere, right? Now if I hold my v constant, like right there, and move my u, I draw that curve. Okay? Put them all together, you get the sphere. So with the idea of being able to draw a surface, we now need to look at what the geometric meaning of a derivative of a vector function like this is. So remember from the vector function of one variable that if you took r of t, you took its derivative r prime of t, it was a vector which was tangent to the curve at a point on the curve. Remember that? So give me a curve, I find the derivative, it's this red vector that's tangent to the curve at whichever point it is. Now, because our new vector function is a function of 2 variables, we cannot take just a straight derivative of it. We can only do like a partial derivative of it. So what we'll do is we will look at the partial of r with respect to u, which means we hold v constant and differentiate it just like we did before. Or we'll do r sub v, which is the partial of r with respect to v, where we hold u constant. each one of those will give us individually a tangent vector. So here's that same picture we had before, right? If I go to some point and I hold my v constant, I get this vector, right? Remember, it draws, if I hold v constant, I just draw a curve. And since that's a curve, I can find the tangent vector to that curve. If I instead, at the same exact point, hold my v constant, now I'm on that circle instead, and that's just a curve, and I take the derivative of that curve, I get this vector here. The two vectors together mean something, don't they? If you can take those two vectors together, they create a plane, don't they? And that plane should be tangent to the surface at that point. So given a surface S with the vector function r of uv, with uv and d, we can find the equation of the tangent plane at any point on the surface. So this is our first by hand example. Is it time for a break? No? Not yet. So what is the equation of the unit sphere? Okay, the vector equation. Sine u, cosine v, sine u, sine v, cosine u, with restrictions that 0 to pi on u, 0 to pi on v. Right? We just had that previous notes, right? 13.6.4. So how am I going to find the vector, equation of the plane that is tangent to this sphere at the point root 2 over 2, 0, root 2 over 2? Well, think about that plane that we had there, right? The one in the previous picture, that green plane. It was made up of two vectors, right? How do we get equations of planes if we have two vectors in the plane? If I have a vector in a plane, another vector in a plane, how would I get the equation of that plane? Cross product of them, right? And then that'll give me my normal vector. And then I need a point, but I already have a point, don't I? I just need to know what those vectors are. But what are the vectors? They were the tangent vectors to the curves when you do the partials. So all I need to do is find those two partials. Those will be my tangent vectors. Cross them, and we're done. So let me first find the RU. So what is the partial of the vector function r with respect to u? So you do it component by component. You do each one, you go in, you're holding v constant. So this becomes what? Cosine u, cosine v, right? And then cosine u, sine v, and then finally negative sine u. That's my partial with respect to u. Partial with respect to v, negative sine u, sine v, sine u, cosine v, and then what's the derivative of cosine u with respect to v? 0. Now those are the vectors that will run tangent to my surface at a given point. Now I actually need to plug in the point, right? So what do? Plug in. Yeah, I don't want to cross them yet. That would give me, I could do that, but that would give me a general equation of a tangent plane, and that would be more powerful than just finding it at one point, right? But I'm going to do it just at this point. So what I'm going to do is try and figure out what the exact vector is at this point and the exact vector at that point, and then from there I'll cross them. It'll be easier to cross. But my question to you is, how do I figure out what the, like, what's the point here that I'm plugging in? Do I go and I plug in like root 2 over 2 for u and 0 for v? Like, what the hell do I do? Yeah, I need to figure out, this point lives on my sphere, right? Lives on it. And this draws my sphere. I need to figure out the exact value of u and the exact value of v that make that point happen. Right? What value of u and what value of v? Which of those looks like the easiest thing to figure out first? Maybe this one? Cosine of u has to turn out to be what? So I'm going to do this work right here. I need my cosine of u to be equal to root 2 over 2. So where does that happen? Pi over 4. Where else? Three pi. No, not 3 pi, but right. It happens here, right? If this is your unit circle, it happens here, and it happens here, right? Negative pi over 4. But what's our restriction on u? Has to be between 0 and pi, which means the only solution we have is pi over 4, right? So we don't even have to worry about general solutions here. So we know what this is now, don't we? And that's great news, because if we know what this is, don't we already know then what this is and what this is? Yes? So let me work with the next equation right here. I need this one to be equal to what? 0? I think I'll extend this work down here. I need sine u, but I already know sine u is pi over 4, right? So what's sine of pi over 4? Root 2 over 2? Let me write it down. I'm trying to find sine u, sine v equal to 0. Shit, I don't even care about that. I can divide through by sine u, right? Because I know that that's root 2 over 2. I need to know when sine v is 0. So when is that going to happen? When is your at 0, pi, and 2 pi? But what's my restriction on v? Well, between 0 and 2 pi. So it could actually have how many answers here? 3 of them, right? Do you agree with that? So that's not quite enough. Right now I know that v could be 0, pi, or 2 pi. So let me go with the next equation. This one right here. I know that that has to be equal to what? Sine u cosine v must be equal to root 2 over 2. But what did we say sine of u was? That was sine of pi over 4. We already said that's root 2 over 2, didn't we? So this is root 2 over 2. Cosine v must be root 2 over 2. So cosine v must be 1. All right, just divide both sides by root 2 over 2. When is cosine 1? Where? 0 and 2 pi, right? 0 and 2 pi. So v must be 0 or 2 pi. Now, is it going to matter? I mean, look, the only thing that threw something in here that was a little challenging was this right here. The pi, right? This one said, well, it could be pi, and this one's true. But that one's saying, no, this can only be true at 0 and 2 pi. So remember how the spherical coordinates worked, is that the way spherical worked is we pointed out, we did a certain angle, right? And then we went down. This one went from 0 to pi, right? And this one went from 0 all the way back to what? 2 pi. So aren't 0 and 2 pi the same place? I mean, it's the same exact point. So I can use either one. Doesn't matter. So what do you want to use? 0? Okay, so V is 0. Let's pick that one. So here's what I've got. I need now to find the vector that is tangent to this surface at u is equal to pi over 4 and v is equal to 0. Then I will cross that with the tangent vector at pi over 4 of the other vector derivative. This will be equal to the normal vector of my plane. That make sense? The normal vector of my plane is going to be this partial, plug in 0, pi over 4 and 0, crossed with the other one. So let's plug in pi over 4 for u. We're plugging in pi over 4 for u. We're plugging in 0 for v. So you get root 2 over 2 here. Root 2 over 2. The next one you get what? 0, because sine of 0 is 0. The next one you get sine of 0, 0. Oh no, sine of u, pardon me. Yes, you all know where that is, right? Sine of root 2 over 2. Or sine of, sorry, sine of pi over 4 is here, right? So that's root 2 over 2, but then make it negative. So negative root 2 over 2. We're going to take that vector, cross it with, what do we get there? 0. Nice. What's the next one? Root 2 over 2. And the last one, 0. That looks like a pretty easy cross there. I'm going to put this other one underneath it because it's easier to cross that way. Cross them out here. So I get 0. My I, what do I get for I? 0 and then these two, right? Negative, but then negative again. So 1/2. Then that one's 0. And the next one, 0 again, right? So we only get one component for that. That is the, that is it? Oh yeah, it is. What was I doing? 1/2, thank you. That is the normal vector of our plane. So the equation of our plane, I think we're ready to go with. The equation will be 1/2 x minus the x root 2 over 2 plus 0. So this kills the whole y thing off, right? And then plus 1/2 z minus root 2 over 2 again equals 0. That's the equation. Of course, you could scale things out, clean it up, but that's the equation of the plane. What do you think? All right? This brings us to our next concept, which is if we can figure out the plane that's tangent, then we can imagine taking little infinitesimal planes and adding them all up and getting a surface area of the surface. And so what we do is when you have that plane, right? If I want to approximate that little red thing there, I can approximate it with this. Can you all see that? My tangent plane, it's a little bit off the surface. My tangent plane is a little bit off the surface. But if I go small enough with the tangent plane, it'll be, if I go infinitesimally small, then it'll be exactly the area. So what is the area of the parallelogram spanned by two vectors? What's the area of a parallelogram spanned by two vectors? The magnitude of the cross product. So what we do is we take the area of the parallelogram, and then with respect to area, it's a double integral. All right? That's what we have to do to find the surface area. All we have to do is take the cross product of the two partial derivatives, take its magnitude, and then do a double integral over the region D. Now, what's D? It's our restrictions on U and V. So remember how our U and our V live between things? That's what we'll use in our double integral, those restrictions. So find the surface area of the unit sphere. We all know what the surface area of a sphere is, right? Well, we could look it up if you didn't know. Surface area. So let's use this to do that. What are we going to have to compute in order to do this? Partials, right? Which we already did that work, didn't we? So I'm going to go back to the notes I just had. I'm going to grab that stuff that we already did. It was all of this right here. Right, we had done this. This time, though, we're going to need to cross those. Is this the unit sphere? That is, right? Oh, no. This is unit sphere. Why is it unit sphere? Because there's really a 1 in front of these. Remember, they're supposed to have rho in there, but if rho's not there, then rho is 1. So this is the unit sphere. Let's cross these. I'm going to do it right underneath it. RU cross RV is a vector. So let's look at our I component. We get 0 here, then we subtract, so we add, because it's got a negative. What is it? Sine squared U cosine V. Agreed? It's this times this. And then we do the J component, which is going to be this here times this minus this times this, but then I change sign, so plus. It'll be sine squared U sine V. And then last, to get my K, cover this up. Cosine U sine V. I said sine V, I meant sine U. And then cosine squared V. That's the first part. That's just this times this. Then minus this times this, but then it has a negative, so it'll be plus. So plus, what do we have there? Cosine U, sine U, sine squared V. The last one there, things do get good, don't they? A little bit. You can factor out cosine U, sine U from both. And what would you be left if you factor that out from these two? You get a 1 there. So that last component is really going to just turn out to be cosine U, sine U, right? That whole thing is just that. Now what do I need? Magnitude, right? Magnitude of this. So the magnitude is the square root of each of the components squared, right? The sum of each of the components squared. So this gives me sine to the 4th U cosine squared V plus sine to the 4th U sine squared V plus cosine squared U sine squared U. I heard woohoo, I think there was. Okay, because that sine to the 4th U comes out of both of those. If I factor that out, this is cosine squared V, sine squared V added together, so we get 1. So that's just a sine to the 4th U, and then plus cosine squared U sine squared u. What can you do now? Pull out a sine squared u. You'll be left with sine squared u plus cosine squared u. But that's 1. So this is just square root of sine squared u, which should just be sine u. Right? Sine u. So now we want to find the surface area of the whole thing, right? So I'm going to create a double integral. Remember what our restrictions were. U went from where to where, and V went from where to where? 0 to pi here, and 0 to pi here. So in here I've got sine u, right? That's the magnitude of the cross product of the partials. We're doing this with respect to area, so I'm doing it using those two limits of integration. So since they're both constants, the order doesn't matter, does it? So I go, now this does matter. I have to put dv du, right? What's the antiderivative of sine of u with respect to v? V sine u, right? Plug in 2 pi, plug in 0, and you just get 2 pi sine u with respect to u. Antiderivative of sine u is negative cosine u, is that right? So negative 2 pi cosine u evaluated from 0 to pi. Plug in pi. What's cosine pi? Negative 1. Negative 1 times negative 2 pi is 2 pi. What's cosine of 0? So I'm going to go minus, and then now plug in 0, I get cosine of 1, so that's negative 2 pi. So you just get 4 pi. What is the formula for the area of a sphere? That's volume. 4 pi r squared. Now in this case, r was 1, so it came out to be 4 pi. But you could do this entire problem. You could start it all the way from the beginning, and you could have put like rho into this, right? Rho, rho, rho. And then you could have done your cross, but you would have a bunch of rows in here. And then when you simplify all this, you would have a rho in your integral. And then when it all works out, you would get 4 pi rho squared. All right? Now you may say like, well, we already had that formula, so who cares? But now you can imagine you could take any portion of that surface and find its area. You don't have to do the whole thing. You could just take a certain slice of it and do it. Is there a question?
So you do the cross product, you get this area from the parallelogram, and you multiply it by small change. I'm just trying to get an idea for...
The differential is, do you remember when we were doing work, and what we started with was this tangent vector, this unit tangent, right, vector, but we had to scale it by the arc length to make it. Do you remember that?
Yes.
Same thing here. We're taking the parallelogram area, but those vectors, right, they don't have to be infinitesimally small. So that dA is the way of scaling it back down to be scaled properly so that it gives you the little infinitesimal patch area instead of this big old friggin' area sticking out of the sphere.
I guess, so it is, I mean, it's kind of interesting it wasn't a Jacobian, because we are on our infinitesimally small change it exists only on the surface of the sphere, so it'd be like this curve thing, right? Well, I guess not, because it's tangent at some infinitely small.
Yeah, that's the idea, is that because it's tangent, as you get smaller, the approximation approaches the approximate area approaches the true area. And with our number system, we have the idea that if you have a limit, if you have a sequence of numbers that's approaching something, converging, it can only go to one place.
So essentially, this tiny DVDU is a little square.
Yeah, you can look at it as a little square. It's scaling back. The du is scaling back the partial with respect to u. That vector, it's scaling it back. And the dv is scaling back the partial with respect to v so that they are infinitesimal instead of just arbitrary vectors. Yes. Yeah, that's what this picture was supposed to illustrate. Is that that's the idea of we can get the plane, tangent plane. See, those are the vectors. This is the partial with respect to partial with respect to u, partial with respect to v. If I take the magnitude of those two, it's just the area of that big old thing. There's no way that's an approximation of the infinitesimally small little patch there, right? So what I do is I scale it by where is it right here? I scale it back using du dv. So there's where I start with, and then I go infinitesimally small, bring in the du dv, and it starts to bring those vectors in to approximate that red patch. All right, now, here's the equation. There's your equation, right? For surface area of a general surface, right? But if you have, we studied surfaces in the very beginning where we said we had a surface that was given to us by a graph of a function, right? We started out very beginning, functions of two variables. There were these surfaces where the domain lived on the ground. These parametric surfaces, you draw these surfaces, the domain is not anywhere that you can visualize. It's like time in the background. Right? When we were drawing, you know what I'm talking about? Like the curves we drew in space, time was our independent variable. The curve went along. You never saw time in the picture. With our parametric surfaces, drawing the sphere and stuff, our domain, u and v, is background. We don't see it. But here, when we had z as a function of x and y, we had the surface where all the z values, the x and y on the ground was our domain. We could see them all together. So in that case, that we can, if we have a case where we can just look at z as being a function of x and y, then we can say, okay, x is x, y is y, and z is some function of those. In other words, our x component of our vector function, the surface, we can let x be u, let y be v, and then we can let z be some function of those two. And what's nice about that is if you do that, and you do the cross product of the partials, you get this. The magnitude of the cross product of the partials. Do I need to show that or not? I mean, look, this is the vector. Imagine this. This is the vector. U, V, and then Z of UV. I guess I'll show it. If I have this, R of UV is U, V, and then I'm going to say some function of UV. I don't know what it is. If I asked you for the partial with respect to U, what would you say? 1? No, that's a V in the middle. 0. And then whatever the partial of Z is with respect to U, right? That's what I get there. And then what about with respect to V? 0, 1, partial Z with respect to V. Now, if I say cross those two, right, cross them, what are you going to get for your first component? Partial Z respect to U, right? Yes, negative. Thank you. And then what about the I? Partial Z respect to V, and then what about the last one? Oh, did I change sign? And then last one? 1. And then now the magnitude, right, of this is just going to be square root of, I'm going to do a different order, 1 plus partial z with respect to u plus partial z with respect to v squared on both of those, right? Which is what this is saying. Instead of saying that my z is a function of u and v, my z is a function of x and y, then it's partial of f with respect to x instead of partial of z with respect to u, and then here, same thing. Which means if we want the surface area, if you're given a surface that's a function of x and y, all you have to do is integrate this over its domain, the shadow on the ground. Make sense that that would be that way? So find the surface area of the paraboloid z equals y squared minus x squared, which lies between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 9. This is a nice problem. We have this weird bent washer, right? We want to know the surface area of it. What's its surface area? Well, is the, and do y'all see the center of it's been popped out? Y'all see that? So the first question you should ask yourself when we're dealing with surface areas is the surface that you're looking at a function of x and y only? Well, in this case it is, right? It's y squared minus x squared. So this is the special case that we just had. So here's what I'll jot down here. I know that my z is y squared minus x squared, which means that I have a function of x and y. So what I'm going to need to do to find the surface area is I'm going to need to do the double integral over d of the square root, right, of all that stuff. So square root 1 plus partial f. Can I say partial f with respect to x squared like that? Partial f with respect to y, that better? Notation, a little shorter. dA. However, my region on the ground is a little weird, isn't it? It's when we look at this, that region is perfectly suited for a polar coordinate system, isn't it? Isn't that perfectly suited for polar? So I think I'm going to have to convert this whole double integral into polar coordinates, which means I have to change all my x's and y's and everything else. So, but before I do that, let's go ahead and get partial f with respect to x. What is partial f with respect to x? Negative 2x. Partial of f with respect to y? Negative, just 2y. And then I plug those in there, right? Double integral over d, square root of 1 plus 4x squared plus 4y squared dA. You all agree with that? Now let's go take care of this region. What are the radii here that I have? So, was it 1 and 3? So describe to me this polar region. I'm going to convert all my x's to r cosine thetas, all my y's to r sine thetas. My theta is going to be between 0 and 2 pi. My radius is going to be between 1 and 3. Make sense? I mean, technically, we could actually have been working with like u and v's here if we wanted to. But we've done so much with polar conversions using this, we just want to stick with it. I'm just going to stick with it. All right, now if we do that, then how does this double integral change? We go from 0 to 2 pi, how about that? 1 to 3. Square root of what? Well, this is 4x squared, 4y squared, right? Pull the 4 out, you get x squared plus y squared. Isn't x squared plus y squared r squared? Yes? So isn't that just 1 plus 4r squared? So square root of 1 plus 4r squared, r dr d theta. Good thing that r is there this time, huh? That's going to help with the integration, isn't it? Basic substitution. There's a derivative of it, kind of, and then you can just go from there. I think at that point, it's just work it out. Questions, though? Break? Okay. Back to the fun stuff. All right. That does it for chapter 13, section 6. So we're moving on to 13.7. There's only 2 sections left in the book. Hopefully it'll be more questions than anything else. We'll see how things go here. Okay, before I start this, there's one more parametric surface that I want to discuss with you. All right, one more parametric surface. Let's say we just have a plane, but not a plane that's parallel to any of the coordinate axes. So say it's like x plus y plus z equals 1. Then can I come up with a parametric equation that will draw this plane? Restrictions on u and restrictions on v. Well, here's one way to do it. If I come up with the vector, I'm just going to draw it like this. It's running parallel to this edge here, but it doesn't have to. It's just, I just drew it that way. And then I'm going to draw some other vector, which just happens to be parallel to the other edge, right? Those are 2 vectors that live on that plane. I'll call this one u. I'll call this one v. You know what? I better not call it u and v. Let's call it w. Okay, s and t. S and t. I have 2 vectors there, right? Each of those vectors draws a line, right? Like if you extend them forever. Yes. So if I picked like an initial point, let's say that's some point x naught, y naught, z naught. Then if I take x naught, y naught, z naught, and I add to it all multiples, C is going to be my scalar, all multiples of s, wouldn't I draw all this vector in a line going in both directions forever? Right? This is kind of like, remember the vector equation of a line was r of t equals r naught plus tv. This is like the same equation, but this is our R naught is a point in 3 space. Our T is a constant, and then S is a vector, our direction of that line. That'll draw that one, right? Now what about the T? What if I were to have taken this and replaced it with some other scalar, let's say D, and then the vector T? Would that draw the line that way? So how about I tack that on to the end of this equation, plus dt like that. Then if C is 0, I draw everything going down the T vector. If D is 0, I draw everything on the S vector. If D and C vary, I draw every linear combination of those two vectors, meaning I would draw maybe a vector that came out this far on T and a vector came out this far on S, put those two together, and I would be here. Linear algebra people might interpret what I'm saying as these two vectors span the entire plane. Therefore, they create the entire plane. So this is now a new equation for a plane. It's a vector equation. So here's how we could write it in a little bit of a better notation, because this was just to get you to think. Here's the way we can write it. I can write R of UV equals R naught, that would be my initial point, right? Plus UA plus VB. I'll draw a picture next to it so we have kind of a better one. This is my vector A. This is my vector B. And this point right here is the point that comes from R naught, right? So A and B have to be vectors we're given, right? They're the directions of the plane. They're two vectors that live on the plane. They do not have to be perpendicular, but they cannot be parallel. Because if they're parallel, they draw the same line, and then you don't draw the plane. And then the U and the V are just scalars, aren't they? Those are our scalars. And so if I want to draw the whole plane, I let U and V vary between what? The other way too, though. Negative infinity to infinity. So we would just say U and V are both elements of the real numbers, all real numbers. So that should give you the entire plane. Does that make sense? Okay. The things that would have to be given, which would be hard numbers in the problem, this vector right here, that you would have to know what that vector is, right? Here, that vector you'd have to know, that vector you would have to know. Yeah, let's do an example real quick, all right? So let's say that we have this x plus y plus z equals 1. I want to convert that into an R of UV. All right, so first of all, I need an R naught, which would correspond to any point on that plane. How about 1, 0, 0? That's a point on that plane. All right, how am I going to get a vector on that plane? Because I need my, what did we call it? I need my A vector and I need my B vector. So I have this point, 1, 0, 0. Give me another point that's on that plane. 0, 1, 0. Give me another point that lives on that plane. A 0, 0, 1. None of that stuff. All right, so I could just do this vector is A and this vector is B. So what's A here for us? The vector negative 1, 1, 0. The vector B is negative 1, 0, 1, right? Y'all following me? So what is our R of UV then? R of UV is R naught plus U times A, which was negative 1, 1, 0, plus V times B, which was negative 1, 0, 1. And if we combine these together, which means we distribute the scalar through, and then combine all components, we get this. What's our x component? 1 minus u minus v. Our y component, just u. And our z component, just v. Got it? This draws the plane. Anybody see another way we could have done that? We could have solved for z up in this equation, right? Say z is determined by x and y are free to be anything. Why? Because the plane, if you look at the shadow of the plane on the xy plane, it's everything. I'm just showing you a way you could do this. It's not the only way, but I thought this would be the best way to get it visually, to be able to see that all we're doing is taking two lines and then looking at their span, two vectors that, what their span is. All right, now we can move on. All right, surface integrals. The surface integral of f over s. I should probably pass something out before I go any further. Chapter 13 has lots of formulas. In fact, 16 pages worth of formulas. So I've printed this out. You can use this on your test. This has pretty much a summary of everything in Chapter 13 as far as formulas are concerned. You just have to know which one to use, I guess. Well, I don't go filling it up with a bunch of examples, because that you couldn't use on the test. I prefer you leave this alone unless I tell you to put something on it, because then that opens that whole gray area of, I walk by on the test and you got all this writing on this thing, and then I'm wondering what that is. And no, that's just, you can just have that. So if you look at this, formula-wise, go ahead and look at this 16-page thing real quick. The first page, all line integrals. The first one, line integral with respect to arc length, then with respect to x, then y, then some notation, how changing the direction changes the value. Then you do line integrals on third page, line integrals in space, which means we went to three-dimensional curves. And then you get to page 5, line integrals of a vector field along a curve. We had the definition of that. We had some notation on page 5. Page 6, fundamental theorem of line integrals. Path independent stuff. The test that we use to see if something's conservative, if it's two-dimensional. Page 7, Green's theorem. Notice in Green's theorem, most of these, I don't put what the conditions are. I'm just giving you the formula, right? I wouldn't have enough space to put like, okay, Green's theorem is only true if the, partials are defined and all that stuff, right? Took all that out. Okay, curl, what the actual computation of curl is. The curl of the gradient of f is 0. If the vector field is conservative, then the curl, if the vector field is conservative, then the curl is 0. What else? Divergence is on the back of the next page. Vector form of Green's theorem is something I mentioned at the end of class last time, or sometime in class. I think it was towards the end. And then I think we're going to get to, parametric surfaces. So common parametric surfaces, planes, that's what I just gave you. You can check if you want to draw a cylinder. Your cylinders would look like something like those. Sphere, general functions, tangent planes. I already see a typo on tangent planes. Page 12, where I say note R. See that? R, that's partial of R with respect to U, And then the one below it, it says V. That should be what? Partial of R with respect to V. Surface area, that's what we just did, right? The one below it is if your Z is a function of X and Y. And now on page 13 is what we're going to do now, all right? Surface integrals. So given a scalar function on a surface S with vector equation of the surface given by R of u v with u and v and d, we have the double integral over S of the scalar function with respect to capital S is equal to this thing. Now this is very difficult to visualize because what you have is you have a function that it needs three things to actually spit out an answer. It needs an x and a y and a z, right? You give this function an x, y, z, it spits out a value. So like maybe that function tells you the temperature at a certain point in the room, right? And then what you have is you're only looking at that function on a specific surface. So imagine now that in this room we have a sphere. That's surface in this room, right? Three-dimensional space. And then we can look on the surface of that sphere every point and look at what the temperature is on that surface, right? The surface integral of a scalar function over S is basically going to add up. It's going to take, so like you're on the sphere, right? You have a certain temperature, right? You're going to take that temperature and you're going to multiply it by this. What's this? Okay, here's my picture. Let's say we have a sphere, right? And then we take a point on that sphere, like this, and then we have its temperature, okay? Temperature at x, y, z. This whole surface right here, this whole sphere is S. That's my surface. Well, that's not a very good S. That's S, right? This surface integral is actually integrating that thing, okay? This temperature function evaluated on the surface, and then it's multiplying it times that absolute value or magnitude of the cross product dA. So wasn't that the infinitesimal area of a little patch right there? So imagine taking a little patch on that, bring it over here, put it on the ground. Then isn't the temperature at that point, you could look at that as almost being like the height of this thing? So you just imagine you just got like this cube, right? This three-dimensional solid. And you're adding them all up. Yes? Wouldn't that give you like almost like a net temperature, like a total temperature on this thing? Does that kind of make sense? You could also look at it like, there's a charge on a surface or something, your total charge. Or if that represented your density, then that would be your what? If this was a density function, that'd be the mass of this thing. See what I'm getting at? It's just adding up. It's not just taking the x, y, and z coordinate and just saying, oh, what's x, y, z? It's saying there's some function there, some scalar. Maybe it's temperature, maybe it's your density, maybe it's your electric charge, whatever it may be, and you're adding up all of them along the surface. So you get this total. But to add them up, you need to, you can look at the little area on the ground and then the height of it. That gives you a nice value, right? You have like a volume of this. I hope that makes sense. Okay, so here, what's that? Okay, my battery's dying here. Thank you. Find the surface integral Find the surface integral of xyz ds, where S is the part of the unit sphere above the cone, z equals square root of x squared plus y squared. So they give us the scalar function. It's in here, right? This is my scalar function. This is my f of x, y, z. It's just x, y, z. And then I'm trying to figure out a way to find the parametric representation of this red cap. It's on the sphere, but it's above the cone. So it's only this red part of the cap. So what's the parametric curve, the R of UV, that gives me that cap? And just that cap. Is that a unit sphere? Does it say unit sphere? Yeah, it says unit sphere. So how can you draw me that cap? Okay, so we already know that the way to draw the unit sphere with a vector was what? We did this before, sine u cosine v sine u sine v cosine u, right? We did that in the previous section. U is between 0 pi, v is between 0, 2 pi. That draws the whole thing, doesn't it? Is that what I want? Is that what I want? No. I just want that top cap, right? So how am I going to figure out that top cap? Okay, yeah, that's a good idea. Why don't we take that sphere here, and imagine cutting it right down the center. Just slice it down the center, peel it open, look at it from a cross-sectional view. And you would have the cone, and then you'd have the sphere, right? Now let's see where I'm going with this. So here's my cross-section. I know my radius here is 1. My cone is coming up and doing this, right? And they're hitting. What am I most interested in here? The angle. Why? Because in spherical, doesn't that tell, like, right? My angles, in this case, my v is my 0 to 2 pi, right? And my u is 0 to pi down here. If I only want to draw the top cap, then all I want to do is move this back and forth, right? And turn as I go back and forth. And that'll draw me the cap up there. But I need to know what this angle is that I come down to. I can't go all the way down to pi. Am I making sense? So the question is, what we're getting at with this is, what's that angle? Well, you know that the equation of this guy, the cone, was what? Z equals square root of x squared plus y squared. But if I came in here and did a cross-section and sliced it and looking at it from the side, then this axis, well, the up and down is my z-axis, right? This axis is what? Either my x or my y, depending on how I sliced it, right? Which means one of the variables, like if this is x and this is z, I sliced it down the middle. What's y then? On this cross-section, what's y? 0, because I cut it right in half, right? Do you agree? So if y is 0, go up to this equation, and this becomes z equals what? Square root of x squared, which is x. Or actually absolute value of x, but we get the idea that that line here is actually z equals x, which means this angle is what? 45 degrees, or pi over 4. See that? You understand that? Now, what if it wasn't that? What if it was, and just for the sake of argument here, what if it was z was 2x? Well, then you would have something that looks like this. It's twice as steep, right? So this is 2x here. This is x here, right? Whatever x is, that's 2x up there. So you could actually come up with a right triangle here. You could figure out, you know, this is the radius. This would be 1. You could actually come up with a trig function to find this angle, right, using these sides. I mean, right now, our sides are what? If it's whatever x is, that's what z is. So these are the same sides, right? So if you did like arctan of x over x, you would get 45 degrees. Well, if you had different values here, then you have to arctan, you would get a different angle. But that's how you could recover the angle if you needed to. The only reason I'm saying this is because I swear I've seen a problem that I've given to students before where the angle wasn't 45, that they actually had to compute the inverse tangent to get the angle. I don't remember when, but I know it's happened before. So, okay, so that should get me. If I just swing my which angle? Which angle is this? Which is the one that's between 0 and pi? Yeah, we're using u, right? So we want this angle right here to actually go between where and where? 0 and pi over 4. And then what about the v? I do want to rotate all the way around, right? I still want to keep going all the way around. So the only modification I'm going to make to this is that I'm going to let my u go between 0 and pi over 4. Questions? All right, so I have my parametric surface. I have its restrictions. And now I'm trying to evaluate this thing here, right? So what is it that I need to evaluate that? I need to take the vector function and plug it into the function itself, and which we talked about what this really means, right? We take the components and then plug them in, and then here, what do I have to do? Unfortunately, take the partials, cross them. Did we do that already? Didn't we already do that? Didn't it come out to just be sine? Did it? Or no? Was it sine u? Let's just double check that is exactly what we did, right? It was this one right here, right? That was the vector function, exactly the same. Crossed them, took it, we got sine u. All right? So I'm not going to go through that work again, obviously. So I'm trying to do double integral over s of f of x, y, z ds. This turns into a double integral. Notice in the formula, double integral over d. So you're taking your double integral over your surface area, and once you convert this ds into that magnitude of the cross product and all that, dA, it becomes with respect to d, which is the restriction on u and v, of f of r of t, or sorry, r of uv, and then times the magnitude of r partial crossed here, dA. Is what that comes from, that Jacobian determinant that we did talk about, right? We did Jacobian determinant. That's where it comes from. In this problem, it's only popping out here because we're doing a surface integral. Anytime we would do a surface integral on a sphere, we would always have that pop out. Sphere radius 1. So help me out with this. What does f of r of uv mean? Well, the f function was x, y, z, right? So I'm replacing x with the x component of my original vector function. So it's sine u cosine v, right? Replace the y with this. Replace the z with this. So it's just all those multiplied together, right? So let me do it. This will be double integral over d of, what do we get? Total, when we multiply all these together, what do we get? Sine squared u, right? Sine squared u, sine v, cosine u. Sine squared u, cosine v, sine v, cosine u. And then, that's this part. Then all this right here, we don't do that work because we already did. That's sine, was it u? Yep. And then finally, dA. And this is equal to, now I can put my limits of integration. They're both constants, right? So it doesn't matter which order I go in. I'm going to go 0 to 2 pi here, 0 to pi over 4 here. And then let's group some stuff together here. We've got sine cubed u, cosine u, sine v, cosine v. D, u, d, v. Can't read my own writing here. Any questions? Why is it?
Why
What?
do you multiply the
Components of the vector?
x,
Because the function that we're trying to evaluate, right, f of xyz is xyz. When we say f of the vector function, that means we're going to take the x and replace it with the x component of the vector function, replace the y with the y component, and z with the z component. This is a little bit bass-ackwards. You know, you've heard that before. But if I do a double integral over S, or a surface integral of 1 ds, what do I get? The surface area, right? But we already did that, didn't we? So imagine that your function here was a 1. Then doesn't this just give you surface area? Usually in the past what we did is we did all these integrals, and at the end I said, oh, but if you let that be 1, then you get the volume of the solid, or you get the area of the region, right? This one we actually started with the area to get us to understand what this is, and then we built up the surface integral from there. But now you can see that if you just replace that with 1, it's surface area of S. All right, we're not done with this, right? We could go the rest of the way with this. Because my U's and my V's are completely separated from each other, and because these are constants, I could break this into 2 integrals, right, and multiply them together. So I would have integral 0 to 2 pi. This needs to be my V stuff, right? Oh, no. Yeah? Is it the U stuff or the V stuff? It's the V stuff, right? And what was my V stuff? Cosine, sine V, cosine V? dV. And then I could say times integral 0 to pi over 4 of sine cubed u cosine u du. And then you can work those out, right? These are pretty basic integrals. In fact, what's the antiderivative of sine v cosine v? It's just half sine squared v, evaluate 0 to 2 pi. Yes? This one would be 1/4 sine to the 4th u evaluated 0 to pi over 4. That first one's 0, isn't it? It means the whole thing is 0? It's possible. Because you could have the function have, think about this function's value. All it's doing is multiplying the x, y, and z coordinates, right? As you go around. So the stuff in the first octant gets canceled out by stuff in another octant. Does that make sense? So it makes sense that it could be 0, because you're adding them all up. All right, so that's this one. Okay, so like I said a little while ago, if you're given a surface and you want to find its mass, you just do a surface integral of the density function with respect to S. If you want x bar, y bar, z bar, center of mass, you've got these formulas for it. And this is all kind of stuff we've seen before, right? A special case. Okay, given a scalar function f on a surface S with the equation of the surface given by z is equal to g of xy. So do you remember in the problems we did just in the previous section, we said we could find the surface area of a sphere, but if the surface is something like a function of x and y on the ground, that cross product turned into this. Notice I'm using g here instead of f. That's because the scalar function out here is already using the f. So that's why this changed to a g. So it's just that same formula we just did, except when you, instead of plugging in the vector function, you're plugging in x, y, and then the function of x and y. Instead of doing the cross product thing, you're doing that. So it's the exact same setup, just for the specific case where a surface is a function of x and y. Find the double integral over S of x ds, where S is shown below, the entire surface. That means I need to find the surface integral on each of the surfaces. So I have this blue surface, right? I have to find the surface integral on that. Then I've got this green one. I have to find the surface integral on that. And then, what do we have? The backside. I have to find the surface integral on that. And of course, if we add them all up, we get the surface integral of the whole thing. Right? But to do a surface integral, you have to find parametric representation of each of the surfaces. So you have to find a way of representing this surface, and the backside surface. Can we do that quickly? Let's see how quick we can do that. Everyone understand what we're trying to do? I think I'll grab that picture and bring it. In your notes, it's sitting like this, right? It's a black blob in yours. Copy. Here, I wanted to paste it as a picture. It's going to come in huge. Jeez. I don't know why I can't. There it goes. Okay, here we go. Let's label these surfaces. How about this front one, S1, that back one, S2, and then this side one, S3. Let's start with the easiest. I think S2 is the easiest. Do you agree? Could you tell what the radius of this thing was? Could you tell from my information I gave you? It's 1, right? So the back side of that thing, which is the x-axis, which is the y-axis? Can you tell from the picture? This back side is x is 0, right? Which means this is x, and this is y, and that's z. So I'll just label it just so we're clear. This is X, this is Y, this is Z. So S2, if we look at S2 in 2 dimensions, S2 looks like this. This is Y, this is Z, has a radius of 1. Agreed? And it's everything inside? What is the vector function R of UV for S2? I want to draw that. So what do we know? What's our X coordinate going to be, or X component? 0, because I'm just going to draw this flat thing here. I want to draw the disk, right? That means I need to control the radius and the angle. So U cosine V. And then what about the Z? U sine V. Restrictions on U? V? 0 to 2 pi. All right, let's go for S1 now, unless there's a question. What's S1 going to give me? So if you look at S1 from this perspective right here, it's a circle again, right? It's kind of a circle again. But it's being pushed away and pulled towards us, right? So how can I create that? Isn't it the same thing as we just had, except that the X is no longer going to be just sitting there at 0? The X is actually going to change, right? As I go and try and draw this circle, the X coordinate moves away as I try and draw it. Yeah, what's the X coordinate here? It's 1 minus, this right here, this blue is a plane, right? And it's X equals 1 minus Z. So my X coordinate needs to be 1 minus Z, but what's Z for us? U sine V. So S1, the vector equation on S1 of UV will be 1 minus U sine V, that's 1 minus Z, U cosine V, U sine V. Restrictions on U and V? The same. Last one, S3. S3 is the cylinder, right? We did one like this a little while ago. It's a cylinder. We want to draw the cylinder, except that, so we want to stay at a fixed radius, don't we? Fixed radius of 1. But we don't want what coordinate to be stuck. The X coordinate still needs to change, right? 0 to 1 minus Z. Well, okay, so Y between where and where? Or are we going to do it with the cosine sine stuff? If I'm trying to, again, this is, we can make it hard or we can make it easy. If I'm trying to draw something here, which I don't think, I guess I'm not going to draw anything. Where are my markers? Can you throw me a marker from back there? Okay, heads up, everyone. Ooh, it's blinded there. There's a total luck. Okay, so look, if I'm a point right here, right, I live on this circle, yes? How can you draw points on that circle? Your X is 0 there, right? So you could do Y is cosine V Z is sine V, but no U in front of it, right? See, no U in front of it because it's a fixed radius, isn't it? And then, once I'm here, once I've determined my U and my V, my V, my angle, so I figure out what my angle is, it gets me to here, and then now I need to let my X be between there and there, don't I? Which is between what? 0 and 1 minus Z. 0 and 1 minus Z. Let's see if we can get that together. So S3, R of S3 of UV. I think we all agreed we could say cosine V, sine V here. Then, yeah, why don't we say this one's U? What's V stuck between? 0 to 2 pi, right? But what's my U stuck between? 0 and 1 minus Z, but what's Z? Sine V. Beautiful. Questions? So all we've done is set up the surfaces, right? You can imagine how this might create a significant problem on a test, right? If you have to do a problem like this, set up all your surfaces first, and then do your integrals, which I will just ask you to set them up, but you still have to set them up, because what do we have to do for each one of these integrals? For each of these three surfaces, what do we have to do? We have to do the partials and the cross products and the magnitudes, right? For each one. So maybe we just do one now. I'll let you pick it. Which one would you like me to do? Would you like me to do S2, S1, or S3? S3? S2? S1? See, everyone wants something different. Forget, I'm not going to do any of them then. No. Hey. How about this one? This one looks the most interesting to me. Well, I'm trying to give you an example of one that I guess looks difficult. So here we go. We are going to do the, I don't even remember what it was. It was the surface integral of x ds, but we're actually doing this for what? S1. So I'm going to say S1 ds1. Right? This should be equal to the double integral over d, right, of my function, which my function is just x, right? But my function evaluated on my surface, so I replaced that x with what? The x component of my vector function, which was 1 minus u sine v, but then times the magnitude of the cross product, So I need r. If I just say ru, is that okay? Because I don't want to say r of s1 of u, you know? Is everyone okay? Just, I'm doing the partial derivative of that with respect to u. And it is, with respect to u only, it is what? Negative sine v? Yes. Cosine v? Sine v. Now below that, I'm going to write the partial of r with respect to v, which is what? Negative u cosine v, negative u sine v, u cosine v. Now cross them. When I cross them, I get a vector. First component, u cosine squared v minus minus is plus, plus u sine, oh yeah. All right, and then middle one, that'll become plus. They're both, can't think, that'll become minus. So what do we have there? U sine v cosine v. Then isn't it minus u sine v cosine v? Is that 0? They cancel, right? And the last one, u sine squared v. Please let it be cosine squared v. Minus, but then minus again, so plus u cosine squared v. I'm a happy person now. This is just u, 0, u, isn't it? Now I need the magnitude, which is just u squared plus u squared, 2u squared, square root, root 2u. Yes. Yes, we picked the right one. And now that comes up here, right? That's going to be next to this. That's what was missing up here. So I need to put next to that. So I'm going to, how about I put the root 2 out front, and I put the u up there. And then dA. So this came from down here. Now limits of integration, right? And we're ready to compute it. So what would your limits of integration be? 0, 1, 0, 2 pi, right? And then you would compute it. So on the test, for the in-class test, right, what I would be expecting to see is something like this. Root 2, double integral, 0, 2 pi, 0, 1, u minus u squared sine v, d u dv. That look right? Get those lined up all right? And in front of this, if I had this, right, like this, then it would be equal to that plus the next one and the next one. Right, there's 3 surfaces. So the total answer on the test would be, this would be equal to that first one we just did, plus now you got to go to surface 2 or surface 1, whichever one we didn't do, get that answer, then the next surface. Because remember, the limits of integration are a little different on each one, right? So your final answer would be 3 integrals that you would not have to compute. Does that sound fair to you, that that's all I would ask for on the test? No? How about I just give you like 20 problems where I give you 2 vectors, just ask you for cross products? Yes? Add these vectors, right? Add these 2 vectors. Find the magnitude of this vector. Wow, we still have lots of time. It's 3:30. We have 30 minutes. I said be ready today, right? We're going to go the whole way. All right. 13.74. I tell you what, 13.8 is extremely short. We don't need time for 13.8. It's going to be quick. 13.7 takes a little while to get through. An oriented surface. So we have to talk a little bit before we move on to the next type of integration. An oriented surface is a two-sided surface. There are examples of one-sided surfaces, which I won't get into, but you've probably heard of Mobius strip before, in which the normal vector at every point on the surface exists, and such that the normal vector varies continuously over the surface. With surfaces like these, we can choose two possible orientations, as shown below. So here's a surface. What are those vectors? Normal vectors. What are normal vectors? Orthogonal. So imagine that at each one of these points, we have the derivatives, right? We have the, get off of here. Oh, no. What happened? Oh, no. Just don't stop my video, please. There it goes. Okay, so at each one of these points in here, since this is a parametric surface, we had the partial of r with respect to u, partial of r with respect to v, right? The two vectors. And those two vectors came out and created like this little tangent plane, correct? This tangent plane. If we have two vectors and we cross them, that gives us a normal vector, right? So the black vector is the normal vector sticking out of the plane, the infinitesimal plane at each of the points. Yes? Okay. So if you look at all the points, they have normal vectors, and they all point out of this surface, right? So we are going to call that positive orientation. And if we switch it, and we look at the vectors the other direction, scale them by -1, they point the other way, then that's negative orientation, they all go in. Computation of the normal vector on an oriented surface. We look at two cases. In general, if general surface is given by the vector function r of u v. So if someone gives you an r of u v that draws a surface, the normal vector is going to be the cross product of the two partials, like we just said. That'll give you a normal, right? And then scale it by what? By its own length, and that'll give you a unit normal vector, right? Then negative n is the same vector going the other way. Now, we do have special cases. Can you see that on yours? Why is this not? There it goes. A special case. So let's say your surface can be written where your z is a function of x and y. So x is x, y is y, z is a function of those. Then it becomes this. Does that look familiar? What did we get when we crossed the two vectors? I gave you that example when we crossed them when it was in this case. Didn't we get this? And then divide it by its own magnitude. And that's a unit vector. So again, we have two: general case, any surface given a parametric equation; specific surface that is a function of x and y. Closed oriented surfaces. If the surface is closed, in other words, it encloses a solid, a sphere closes a solid, right? Then positive orientation is the one in which the normals point away from the solid. So with a sphere, positive orientation, the normals go out, right? An example is the unit sphere. Now we get to flux. So surface integrals, see in the last, what we did right before this is we did the surface integral of a scalar function, right? Of a scalar function over a surface. Now we're doing a surface integral, but instead of having a scalar function, we're using a vector field instead. This is very similar to the computation that we did, the integral we did for work, right? Work, we did a vector field, right? on a line integral, on a curve. Now we're doing a vector field on a surface. So the picture of this is as follows. You go, well, let's look at the formula first. The formula for flux, doesn't this look very similar to the line integral over C of f dr, where r was the vector? That was work. Now it's the double integral, because we're two-dimensional instead of a line, it's a surface, so double integral over S of f, our vector field, dotted with not r, but S. Now notice the capital S has a vector on it. All right? That's the notation we use for flux. Now here's another representation of it, where you replace the ds with n, normal vector, ds. Now what's this without the vector on it? What's ds without the vector? And that's capital S, not little s. Surface area, right? So that's, well, some things cancel here. What was ds defined to be? ds was, it was magnitude, right? That was it. That was ds, wasn't it? Okay, so what the hell happened? dA, yeah. What happened here? This n ds turned into this. So what's n? How do we define n? It was RU cross RV divided by magnitude RU cross RV. Too far there. And then what are we doing with that? Multiplying that times ds, but this is ds, right? So multiply that times this magnitude again, dA. These cancel, and so you just get f dotted with the cross product dA. Understand? Okay, so that's the formula. Now, the reason why it's important to look at all of these is because sometimes this formula is easier to use, sometimes this one is. Because the advantage of this formula right here is that you may actually just look at the surface and know what the normal vector is. Like, for example, if I give you a plane, right? If I give you a plane, do you have to go find the parametric equations for it? Not if you know what the normal vector is and you do know the normal vector of a plane. So sometimes it's easier to use this, sometimes it's easier to use that. We'll see as we move on here. Here's the actual idea behind flux. You have a surface, right? I'm going to make this a little bit smaller, or I can make this whole thing bigger. You have a surface. You move around. You try to move around. Okay. I'll do my best to see if I can make this make some sense to you. Okay, the red vector, oh, there we go. Okay, I think we'll use that one instead. Look at this little patch down here. See the little patch? Those red vectors on the four corners of the patch represent the normal vectors to the surface, the ones that are perpendicular to the tangent plane. So those are sticking out, right? Those are my normal vectors. Those are always sitting there, right? Just normal vectors. Then we have a vector field. Now this vector field could be doing anything. It depends on the vector field itself. So on that same corner point, I have the normal vector pointing out, and I have some other vector, the field vector, pointing in not necessarily the same direction. So what we do is we take, and it might be better to look at the one above here. We take the vector field vector, right? And we project it onto the normal vector and create this red vector, right? That's what we do. We project it. And so we get this red vector, which kind of turns it changes your vector field's pointed in this direction, your normal's like this. It says, well, that really has the effect of going in this direction with a different length, different speed, so to speak. And so once you project those on, you take these out, the red vectors here now represent your like outward flow through this patch. And so you add them up, you start doing more points infinitesimally, whole bunch of them, and you get the flow through that patch. A lot of people say, imagine just like a net, and you've got water going through this net. It's measuring the flow through it. So it can be liquid, it can be electricity, different things, right? So they call it flux. Flow through this. Got it? The rate of it. The rate at which it's going through. Yes. Yes? No? You sound like you're being agreeable. I don't want to get into too much of the technical. It depends on the quantity. It depends on what it is. Right? What is it that you're measuring? Is this water fluid flow? You know? So there's our computation. Do we want to do flux? Trying to see how much more we got. We do have Monday. We'll do this one last example right here. I know, but we only have 20 minutes, and I don't think we can get too deep into the next one. Because the next example, well, this one's going to take a little bit of time. Hey, these are long classes, man. It's hard to be in here this long, for you and me both. So find the flux of the vector field of f of xyz equals yzx across the unit sphere. So what we need to do is compute double integral over s of f dot ds, right? That's what we're trying to do. It's the unit sphere, right? So looking back at the formulas we had here, do we know what the normal vector for the sphere is? It'll depend on where we are, though, right? Like where you are on the surface, the normal vector. What I'm getting at is it easier to get this or this? I mean, don't we already did this, didn't we, for the unit sphere? So I think that would be easier to get. To compute n, we have to do that and then divide by its magnitude, don't we? So I think this is easier to do. So let's go ahead and use that third one there. It'll become double integral over d of f dot ru cross rv dA. Now when we say F, what do we mean by F? The field, but the field what? The field, yes? But evaluated on the surface, right? So this really means, we just got to make sure we understand, just like we did the scalar, we had to evaluate the scalar. The last problem we did was x, y, z. We had to replace x with the different parts. This time we're replacing a vector field with it, so the answer will still be a vector. So we're doing f of r of uv dotted with partial r respect to u, partial r respect to v, dA. Okay, take your vector field and plug in. Take your vector field, plug in the vector function for a sphere. So remember, the vector field was y, z, x, wasn't it? What's the y component of our vector surface, our surface, parametric surface? What was the y component? It was sine, was it sine u, sine v? Yep. And then what was the z component? Cosine u. And then our x component was cosine u, no, sine u cosine v. Sine u cosine v. And we will dot that with the cross product of those partials, which we did prior to this, earlier in this lecture today. I don't remember what was it? That was the magnitude. With the cross. That was the magnitude of the cross product, though. The sign, yeah, it was the magnitude. Yeah, I don't remember what the. Okay, hold on. Let me go back and look at it real quick, and that way, see how far back we have to go here. It was this one right here, right? Oh, you're saying that the cross product was the original vector function multiplied by sine u. Okay, I didn't see that when I didn't notice that. Did you all notice that? It's just a pattern, right? Is it? Well, hold on. Well, yeah, there it is. Yeah, it is. Okay, cool. Oh, yeah? You like that, huh? Didn't want to be nerdy. All right, so we've got sine squared u, sine v, sine u, cosine u, and then finally sine squared u. I'm running out of room, so I make my page a little bit. Oh, damn it, I'm out of room. What am I? Oh. It's getting late. No, it was the original. It was the original one. Sine squared u cosine v, right? And then sine squared u sine v. And then the z component, so sine u cosine u. We good? DA? Dot that? Ooh. Okay, we dot it. Double integral over d. Dot it up. We've got sine cubed u. No more vector, right? Sine cubed u. Sine v cosine v. Next one. Sine squared u. Cosine u sine u. Or sine v. Last one. Sine squared u. Cosine u cosine v dA. Don't they all have a sine squared cosine? Oh, no. They all have a sine squared u in them. Don't they? All right. let's not go the rest of the way. I think we all agree this could be done, right? It's not an impossible. You have to integrate with respect to u and with respect to v. So could you integrate this with respect to u? Yes. Okay, because it's separated. Could you integrate that with respect to v? Yes. U and v here? Yes. Basic substitution on that. Same thing here. So I mean, it can be done. What are the limits of integration? 0 to pi, 0 pi, right? Because we're integrating over the whole sphere. And we would have to say d u dv out here. All right. On your notes, I want to see if this was corrected or not. On the next note, 13.78, on your first one up here, you have negative p, negative q, r, right? Then the next one, you have p, negative q, negative r? And on the last one, do you have negative p, positive q, negative r? That's what it needs to be. That last one, negative p, positive q, negative r. It's been adjusted on my notes, but I remember it was a typo on that one the first time I made that. I think what we'll do is we'll pick up there, but let me just show you briefly where we're headed. Okay. Here we can compute the flux coming out of a surface, right? Here we have a solid, right? So you have two surfaces. You got the back of it, you got the front of it. So you want to get the flux on the whole thing, so you have to do two surface integrals, right? Break it up into two surfaces and do flux on each one. Add up the answers. Then you have something that's a little more elaborate, something like this. Well, that's not very much more elaborate, actually, right? Do the flux on that. And then, yes. Three surfaces? Good question. You could not. Only because the vector field here may be different than what the vector field's doing in the back. Now, so this is what we'll do, right? We'll have 1, 2, 3, and 4. So you have to come up with all these surfaces, right? Then what will happen is we'll torture ourselves with that. And then we're going to do 13.8. And we're going to get Stokes' theorem, which says a couple of things. But here's the main result. Whoa. If you're trying to do a line integral around a curve, right? Line integral around a curve. If that curve contains a surface, so imagine you have a circle, right? That's a curve. It creates a disk. Yes? Then you can do, instead of the line integral, you can do the surface integral of the curl of the vector field instead. And sometimes, and a lot of times, that's a much easier computation. Is that all I've got there? Stokes? Yeah. Okay, let's call it a day, and we will come back on Monday. We will have our last meeting. Oh, you know what's missing? I'm sorry, that's why it's not in the notes. The divergence theorem. It's the very last page of the notes I handed out today. That's what we'll also get to next time. It's basically going to give us a way, you know these surface integrals that we're doing right now that kind of suck because you have to do all the surfaces? It's going to say that if those surfaces enclose a solid, that instead we can do a triple integral over that solid instead of doing the surface integral. So that'll be much easier. A lot of times it helps us, yeah. Or sometimes you go the other way. You know, go with the solid and go back to the surfaces. It always depends on the nature of the problem. Sometimes it's easier to go one way, easier to go the other.